this discussion, we're going to be talking about the time value of money, and this is basically another term for interest, compound interest specifically. We're going to talk about such topics as present value, future value, discounting, again, compound interest. We'll talk about annuity payments, lump sum payments, and a variety of different ways to calculate these amounts, as well as different types of problems you could see for these topics. So when we're talking about the time value of money, again, we're talking about compound interest. When you hear the term compound interest, we're not just saying simple interest at a certain percentage rate. We're basically saying that whatever money you put in the bank, for example, it earns interest, and then that interest eventually also earns its own interest. So it's not just having, if you deposit $100 in the bank, you're not only earning interest on the original 100, eventually you'll be earning interest on the interest that was made by the 100. So it continually compounds. So we're going to talk about that. We're going to talk about the relationship between time value of money and inflation. So what we're saying here is that part of the reason that money increases in value over time, or in other words, when you deposit money, why it's worth more down the road, is to account for inflation. That's just a small portion of it. The interest rate we're going to be talking about, again, there are a couple of things built in. Why do we have a certain interest rate that we do? Why is it 3%? Why is it 5%? Maybe 10%, depending on your investment. There are two major components to the interest rate. The first one is the risk. So depending on how risky you are as a borrower, or if you're the lender, how risky is the other side, the borrower, that's going to determine a portion of your interest rate. If you're very low risk, then your interest rate is generally going to be less. But that's not going to be zero in most cases there, and the reason is there's a desired rate of return. So whoever's lending the money wants to make a return. They're not going to give you the money for free. They want to make a return on that investment. They want to make enough of a return to cover any potential risk they may have, but they also want to make a return to reimburse them essentially for not being able to spend that money today. They're putting it aside. They're lending it to you. They want to know how are they going to get reimbursed for that. Not just the original money, but get reimbursed for the time, the opportunity that they are losing to spend that money right now. So that's kind of what's going on there. So just as a quick way of looking at this, dollars today equal more dollars tomorrow. That doesn't mean the same dollar would buy the same amount down the road, and that's where inflation comes back in. If you have, let's say, $100 today, that $100 is not going to buy the same items in 10 years, 20 years. Inflation will wear down the value of that money a little bit. You lose purchasing power. That's part of the reason for inflation, to help offset that and hopefully leave you with a little bit more purchasing power down the road. So when we talk about simple interest, the calculation is pretty straightforward. The principal, whatever your face value was, multiplied by the interest rate. And now one thing I want to mention here, it's the second bullet point. Interest is generally given as an annual percentage rate, an APR. That's just the standard approach in finance to give an annual percentage rate. Even if you're not borrowing for a year, maybe you're only borrowing for 3 months or 6 months, the rate is going to be in an annual percentage rate format, but then you're going to be multiplying by time. I have written here the number of periods. That's if you have more than 1 year. If you have less than a year, let's say half of a year, you would multiply this by half, 1/2, or 0.5. If it's a 2-year note, you would multiply that by 2 years. Again, it has to relate to what the interest rate is given as, and in this case, the interest rate is given as a annual percentage rate. If for some reason you either were given a monthly rate or maybe you calculated a monthly rate, then you'd want to multiply that by the number of months that you're dealing with, or days, or whatever it is. The key thing is your rate and your number of periods have to match as far as what time period are they talking about. So as an example, if you invest $1,000 at 5% simple interest for 3 years, you're going to eventually earn $150 in interest. That's the $1,000, the original investment, multiplied by 5% or 0.05, multiplied by 3 years. Each year you're going to get $50 interest, and you're going to get it for 3 years. Now, keep in mind, that is simple interest. That's assuming it doesn't compound. In other words, the $50 interest you get, it does not get reinvested. You do not earn more money with that. For example, you may be taking that $50 out and spending it on something else. On the other hand, if you take that same $1,000 and you deposit it in a bank and leave it there, all the interest that it earns is left in the account so that it can grow and earn its own interest. If you have 5% interest compounded annually, then our calculation is going to differ a bit. The way I have it listed down here, you're going to earn, for the first year, you're going to earn 5% on the 1,000. For the second year, you're going to earn 5% on the 1,000 plus the interest that you earn in the first year. So the example here, year one, we have $1,000 multiplied by 5% to get $50 per year. The balance at the end of year one is going to be $1,050, so that's also the balance at the beginning of year two. If we leave that money in for year two, it is going to earn $52.50. It had a little bit more money to calculate interest on. So at the end of year two, if we leave all that money in there, we're going to have $1,102.50. Year three, you can see we're earning even more interest. The interest rate is the same, but now we have a larger principal because the interest from last year has essentially become principal now. It's earning its own interest. So at the end of year three, you now have $1,157.63. This is in comparison or in contrast to the $1,150 that you would have had under the original method, the simple interest method. So compound interest does earn you more money. So we could have done this calculation here, listed all 3 years out. It works. But if this was a 20-year or 30-year calculation, we wouldn't really want to do that necessarily. We wouldn't want to break it out and have to redo that calculation every year. So what we're doing here in this section, in this discussion, is we're talking about shortcut methods to be able to calculate compound interest or time value of money through various formulas. We're going to talk about Excel options to use. There are also financial calculator options to use. Certainly there are many websites out there that can be used for this. But we're going to talk about these concepts here. That's basically the discussion for today. So the first concept we have here is future value. We're going to be talking about future value, present value, annuities, all of that. So the future value. This is basically if we know what the present value is today. In other words, today we have $1,000. We want to invest it at a certain rate over a certain period of time. And what we want to find out is what would the future value be. So when you hear these terms, that's telling you what you want to know. You already know other things, but you want to know the future value. You're trying to calculate the future value. So we're basically saying, what is the value of that dollar after including all interest that it will earn over time? So what are we going to have in the future after letting this money sit in the bank for a certain percentage for a certain amount of time? So we talk about that same calculation we looked at earlier, the $1,000 for 3 years at 5%. These are the calculations we had earlier. We ended up with $1,157.63. Now, mathematically, we could have done that by taking 1,000 multiplied by 1.05, which is essentially 105%. The 100 is your main amount, and the 5%, of course, is your interest. So multiply it by 1.05, by 1.05, and then by 1.05 again. 3 different times because we had 3 different years. The shortcut way of doing that, when you multiply a number by itself a certain number of times, you're basically taking that to a power. In this case, the power of 3, the third power. We're cubing it. So it's 1,000 times 1.05 to the third power. So this takes us to our first formula that we could use. Now again, we're going to talk about tables later on. We're going to talk about Excel, but mathematically this is what it all begins with. We take the future value, that's equal to the present value, that's the amount we are investing at the beginning, and we're going to multiply it by 1 plus I. I is the interest rate, so that's where we get that 1.05, 1 plus 0.05, and then to the third power in this example, to the nth power. That tells you how many periods are you compounding this interest for. Now remember, there are a couple of important things here. We're assuming in this discussion that we are compounding annually, therefore it's an annual interest rate. In the world of finance, there are several different types of compounding periods. You could compound monthly, quarterly, daily, and there's something known as compounding continuously. We're not going to really dig into those options here. We're going to talk mostly about the annual compounding. But anytime, if you do have different compounding periods, you just need to make sure your interest rate is in the same period of time. If it's a monthly compounding period, make sure you have a monthly interest rate. So some options. Number one, we're not going to talk about in this course. You could use a financial calculator. There are a few big names for the financial calculators. A lot of these have been around for quite some time. They haven't changed a whole lot. But we're not going to talk about this in this particular section. We will, at the end of the section, talk about how to use Excel. I'm going to show some example formulas, and we'll go through all the various types of questions that we may have there. And then number three, again, we could work it out mathematically, calculate 1 plus I to the nth power, and go through that formula that we had earlier. Or number four, which is in many ways, certainly for accounting classes, this may be the most common. This is using a present value or future value table. So instead of having to work out the math, you look up a table, you're going to find the intersection of the number of periods and the interest rate per period, and you're going to get a factor. So we'll talk more about number four. That's the main component of this discussion. But again, we will talk about number two with the Excel. And we basically already talked about number three. So, future value. We're talking about what are we going to have in the future if we have a certain amount of money today. You can find all of these time value tables, whether it be present value, future value. We'll talk about annuities. You can find these anywhere on the internet. If you search for future value tables, for example, you'll find several examples. I have some screenshots of some that I've used. These could be in your text, in your accounting text, assuming you're taking an accounting course, or you could actually build one in Excel. If you know how to use Excel, you know the necessary formulas. So this is what it would look like. This is table one in this case, the future value of $1. Now, what if we have $1,000? You would multiply these factors by 1,000. So we're starting off with $1. You can see here that we have the same formula that we talked about a bit ago. The only difference is it's assuming the present value is $1. We'll talk more about these tables and why the factors look the way they do. So we have an example problem one. Joey has $1,000 today and plans to invest it in a bank account that earns 4%. She plans to keep it in the bank for 5 years. So the question is, how much money will she have at the end of 5 years? That's a future value. What are we going to have in the future? So to figure that out, we want to know the future value of $1,000 at an annual rate of 4% over 5 periods. So with this table, what you do here is you have to find the intersection of the number of periods and the annual rate per period, or the rate per period, I should say. In this case, it's an annual rate because we're talking about 5 years. So we would find the 5-period line. The rows are the number of periods, the number of interest periods, and the columns are the rates per period. So we would find 5 periods, we'd scroll over to 4%, and now we find 1.21665. So that's going to be our factor that gives us the future value of $1, but we don't want $1, we want 1,000. So we essentially multiply this 1.21665 by 1,000. That gives us a future value of $1,216.65. Now, whenever you're doing these calculations, think about it logically. We know that after earning more interest, we should have more money at the end. A future value should be higher than a present value. And this makes sense. It is higher. It's still relatively close to 1,000. In other words, it's not like we turned $1,000 into 300 million or some crazy amount like that. It still makes sense that it would be about $200 above 1,000. So at least you know you're going in the right direction, and it seems to make sense. As long as you use the right factor, you'll get the precise amount you need. Here in this case, this is just saying that Joey earned interest. She earned $216.65 of interest by putting it in that 4% account for 5 periods. Now let's dig into the table itself to try to get some information out of that. These factors are different for every row, every column, so we want to figure out why are they different. As you can see here, the rate gets higher, or the factor gets higher when the rate gets higher. So this makes sense, as you can see here, regardless of which line you look at, as you start moving to the right, your rate gets higher. The reason is, the higher rate, you earn more interest. So the future value is going to be higher. So that certainly makes sense. Now, let's take any given column and go down the number of periods. It's also getting higher there as well, because the longer you leave money in the bank account, the more interest it's going to be able to earn. It's going to compound more and more and more at whatever rate, and now you've earned more interest. So that's all we're talking about there. You can see here, if we go to the very extreme, 6% and 10 periods in this table, it's 1.79085. So you have a fairly high interest rate compared to the rest of them on this table, and you have a higher number of periods. So you're going to earn the most interest out of these options. So future value tends to be the most common one to look at, because you generally know, hey, we have the present value, we want to invest money, what will we have in the future? You're predicting, it's not really even a prediction, you're calculating what you would have in the future at this rate and this number of periods. Present value is working backwards. Now we want to find out what value we'd have to have today in order to make a certain amount of money down the road. In this example, we know what the future value is. We know what we want it to be. We have to figure out, what does that mean today? So we're still talking about a lump sum. We're going to dig into annuities in just a bit, but we're talking about the lump sum right now. So what is it worth to us right now? In other words, how much would we be willing to pay right now for the right to some larger amount down the road? One good example of when this comes up, and it'll make more sense when we get to the annuity section, but if you look at the lottery, a lot of the bigger lotteries, Powerball is big in many states, they give you a cash option, or they give you what's reported on the billboards. The billboard amount is essentially what you would get if you decide to get this money over time. So you'd have to wait to get this. It's kind of a future value. It's a future value of annuities. Again, we're jumping ahead into the annuity in just a bit, but that's what it would be. Present value is what they refer to as the cash option. What would all this money be worth today if we wanted to cash out today? Another way of thinking about this is that it's the cost of waiting and losing out on potential interest. Again, that for the Powerball, that reported amount is much higher, but if we take the cash today, we lose out on all that interest that the lottery would give us. Instead, we take the money today. We're not waiting. We're taking it today and running. So we're working backwards here. Let's look at the formulas again. Even though we're going to focus more on the tables, let's look at how the formulas work out. The future value factor was calculated as $1 times 1 plus I to get the interest rate. So in our case, 1.05, 105%. And then it was to the nth power. The number of periods we have. Our example was the third period the first time, and I think the last example was the fourth period, or was the fifth period. So that was the future value calculation. If you look at the present value calculation, we're no longer multiplying, we're instead dividing. So in this case, we're taking $1 divided by 1 plus, this should be 1 plus I, my apologies, just like before, 1 plus I, and then we're taking it to the nth power again. The only difference is we didn't multiply that by 1, we divided it, or we divided 1 by it. We divided it into 1. So future value and present value are opposites, they're inverses. One uses division, the other uses multiplication. That's what we're saying there. Using our last example, we already know all of the elements now. We know what the future value is. We know what the present value was. So to illustrate that, we would want to know what is the present value of $1,216.65 over 5 years at a 4% interest rate. If you remember, that was our future value before for a $1,000 present value. And the factor was 1.21665. So now we're just working it backwards. The present value of $1,216.65 is $1,000. We knew all those elements. It's just forward and backwards. So one way to do this is by taking the $1,216.65 divided by the factor that we used last time, which was 1.21665. And if you do that, you end up with $1,000. Or instead of reversing our future value calculation, we could just work it forward and use a present value table, which gives us the actual factors. So notice they have the calculation here again. We're dividing it this time. Notice we still have the 10 periods, the 5% interest rate, but notice all of the factors are now less than 1. Its present value is a reduction factor. We're telling us that our present value is going to be a lower amount because we're basically carving out what the interest would have been. So even at 1 period and 1%, it's still less than 1. Present value is always going to be less than future value. So if we wanted to calculate the present value of $1,000 that we will receive in 5 periods when the annual interest rate is 4%, we need to know what factor to use. Now notice this is not the exact same as the earlier calculation. Here the present value is, or the future value is 1,000. We want to know what the present value is going to be. So we have to take a look at the 5 periods, that line, the 4% interest rate, and now we get a factor of 0.82193. Now notice another way of doing that. Earlier I showed you the forward and the backward future value versus present value. If you divide something by 1.21665, that was the factor we used before, it has the same effect as multiplying it by 0.821921. So go ahead and try that out in Excel or your calculator. Dividing something by 1.21665 works the same as if you're multiplying it by 0.821929. Now notice in this table they round it to the 5th digit. So they round it to 0.82193. So either way, if you for some reason only had a future value table and you couldn't find a present value table, find the factor and divide it by that future value factor. It'll be the same as multiplying it by the present value factor. Works the same way. So that interest rate, if you take the $1,000 minus the $821.93, we're basically saying if we didn't wait to get this money, we would lose out on $178.07. If we want it right now, then we're losing out on that potential $178 in interest. Now let's dig into the tables again to see how these factors change. It's the exact opposite of the future value. The present value factors get lower when the rate gets higher. And what we're saying here, if the rate gets higher, then there's more interest that would have been involved, but you're losing out on it by not waiting. So this actually should say by not waiting for the money. If we wait for the money, we're going to be having that interest, so it's going to be built in. We'll have more money. But if we don't wait for the money, that's where the trouble comes into play. So the rate gets higher as your interest rate gets higher. I'm sorry, I'm backwards there. Your factor gets lower as the interest rate gets higher. And the reason is you're going to be multiplying that by that lower number, and your present value becomes lower. As the number of periods increase, your factor is going to get lower as well. The longer you are waiting, or I should say the longer you're not waiting, you're losing out on interest by not waiting. So in this case, let's take a look at an example. Joey wants to buy a bike that costs $1,216.65 in 5 years. She has a guaranteed investment that will generate a 4% interest. How much money does she need to invest today to be able to have the proper amount in 5 years? This is the type of problem you'll see when we're looking for a present value. You know what the future value is. In this case, it's $1,200. We want to know what the present value is after carving out the interest. Because if we don't wait, we're losing out on interest. So we want to know what today's value is. What do we have to invest today to be able to generate enough interest to get us up to $1,216.65 down the road? So when we talk about these, it's all about what do we know and what is the problem really asking for. If they already give us something that we're going to have in the future, they have already given us the future value, so the problem may be a present value problem. We're searching for the present value. So you'd want to make sure to use the proper table for that. If you already know what you have right now and you're looking for what you're going to be able to invest it toward, what amount will you have in the future, then we're solving for a future value type problem. Now, we've been talking mostly about simple future value, simple present value. We knew the interest rate. We knew the number of periods. We were just looking for the beginning or ending result. In some cases, you may need to find other things. Maybe you don't know what the interest rate is. You know everything else, but you don't know what the interest rate is. Or perhaps you don't know the number of periods. So you may be searching for those. You could, if you don't know, if you're missing just one item, you could go back into the equations and solve algebraically for the one variable that's missing. However, I'm going to show you another approach. Excel has a variety of formulas that you can use to calculate things like future value, present value, number of periods, interest rate, and as we'll get into in a few minutes, payment. So when we start talking about annuities, we're talking about actual payments. We're not saying we have one lump sum. What lump sum is it going to turn into, or vice versa? Now we're talking about starting with 100, adding another 100, adding another 100. How much will we have eventually after so many periods? That would be the annuity. Again, with these advanced methods using Excel, we can calculate payment as well. And that takes us right into the annuity discussion, lump sum versus annuity. So here we're talking about the lump sum versus annuity. Lump sum is one payment. You know the present value. You want to find out the future value or vice versa. Annuity is when we have multiple payments. So we have $100 here, $100 the next month, different periods of time. To be an annuity, it has to be the same amount every period, and the periods have to be the same length. If it's anything other than that, it's not an annuity, and you would have to treat each payment as an individual amount, an individual lump sum. So that third bullet point here is basically telling you you could do that even if it was the same amount, the same period of time. You could treat every single payment as its own lump sum and calculate its own future value and then add all of them together down the road. You could do that, but it gets kind of cumbersome when you have 20, 50, 100 periods. So a table makes it a lot easier to deal with. We have tables for present value of an annuity, and we have tables for future value of an annuity. There is one additional term I want to mention here. We have something known as an ordinary annuity and an annuity due. An ordinary annuity, by the way, there are tables for both of them. An ordinary annuity is when the payment is due at the end of the period. It's either due or the payment is going to change hands at the end of the period. An annuity due means the amount is due right away. So the only difference between the two tables is that you lose one period. An annuity due means that money is not earning interest because it was paid right away. It depends on which side of the equation you're on. Are you collecting the money or are you paying the money? But the annuity due means the payment changes hands right away. So if you're adding it in, if you're paying money and you're wanting to know how much is it investing, how much is it earning, then the annuity due means that had one more period to calculate interest over. The annuity due, the payment was made right away, so it's in the bank a month earlier than it would have been under an ordinary annuity. That's the one thing to remember. That's, in fact, the only difference between the two tables is that the annuity due has one more period of interest. So we'll see these two tables here. The present value of an ordinary annuity. So what we're saying is if we have money going in over time, and by the way, your example of the lottery, the Powerball I was telling you about, this is where it really fits in, because the Powerball is paid out in an annuity. I don't recall if it's 20 or 30, maybe even 40 years. You get whatever that, I don't know, I think the last one was $1.6 billion. You get that split out over, let's just say 30 years, and you get whatever that is every year, the same amount every year. So it's an annuity that's being paid out over time. If you wanted to know the present value of that, you could calculate the present value of each and every one of those payments, or you could use this table. So what we need to, the table is basically the same format, the number of periods, the interest rate, same format. The differences, our factors, are going to look quite a bit different. The first line, some of them are actually less than 1. Everything else, though, every other line is greater than 1, in some cases by quite a bit. What you multiply this factor by, when you find the factor for your problem, is you multiply it by one payment. One interest payment, one of those annual lottery payments, whatever example you want to use. So you multiply this factor by that amount. Not the sum of all the payments you're ever going to get, just by one payment. So let's take a look at what that means. We said that present value is always going to be less than 1. And you're looking at this table, you're saying these are not less than 1, which is true, but they are less than the number of periods we're talking about. If you have just one payment, then these factors are going to be less than 1. But if you have two payments, and you're only multiplying this by one payment, you should expect these to be less than 2. If you have 3 payments, these are going to be less than 3. 10 payments, these are going to be less than 10. So that's what to look at there. Now, again, it's present value. So if you're taking the money and running right now, you're losing out on the potential for interest. So the higher the interest rate, the more money you're losing out on. So the lower this factor is going to be. Because, again, you're multiplying some payment amount by a factor. The lower that factor is, that means the less your present value is going to be. So here's the example I gave earlier. At 2 periods, the factor starts out a little bit below 2, and then it decreases as your interest rate decreases. So that's the present value, where we are reducing a value by carving out interest, so to speak. Future value, we are adding interest in. So we're paying money, we're investing $100 every month into our bank account. We want to know what this is going to be worth in the future. That's basically the type of problem we have here. The future value of an ordinary annuity, again, we would find our factor, whatever intersection we have, multiply this by one payment, and we would know what all these payments are going to be worth in the future after they've been invested. So at two periods, the factor starts out just a little bit above 2, and the higher the interest rate, the higher that factor will be. So it's the same basic idea as the present value, only it's in reverse. So this is what I was getting at earlier, the ordinary annuity versus the annuity due. The only difference between these is when the first payment takes place. With an ordinary annuity, the payment's due at the end of the period. With an annuity due, it's due at the beginning of the period. So essentially, the way to think about this, because if we're talking about a payment due right away, no time has passed, a payment's due right away with the annuity due, it's the same thing as saying we have an ordinary annuity plus we have the first month as a down payment. That's another way of thinking about it. So you could actually use your ordinary annuity table, if that's all you had, even though you have an annuity due problem, you could take your ordinary annuity table, figure out the value for that, and then just add on one payment. You don't have to multiply it by anything, just add on one additional payment at the end of your problem. Now, with that, I wanted to talk about the advanced formulas in Excel. I actually have an Excel spreadsheet I'm going to bring up here. This should give you an idea of how to use Excel for either just normal present value or future value, or for actual advanced problems like finding out the payment, finding out the interest rate, finding out the number of periods. So feel free to use these formulas and try them out in Excel. I'm going to give you an illustration here in just a second, and we will talk about it. So what we have here is an example of a spreadsheet that I've put together to illustrate these various functions. These are in Excel. So we're going to talk about each of them. I'm going to try to focus on each one individually. So if we want to solve for future value, first of all, what you would see in Excel, if you started to type in equals FV parenthesis, this little section down here would pop up. So I'll show you that just right now. This is what's going to pop up. It tells you what it expects. It expects a rate. It expects the number of periods related to that rate. It expects a payment, a future value, and then a type. So I'm going to get rid of that. Now, you could very easily put in your actual amount. Instead of what I've done here, I've referenced cells where I put in the amounts. You could put in your 12% right within this formula and your 6 periods right in there, your payment, all that. But I like to illustrate it by creating lines or cells that show you what the rate is, what the number of periods is, and then I reference to that section. So for this example, C6 is my rate. It's the first item in the formula. That's my rate. Here's C6. I've typed in 0.12. My number of periods would be C7, which is right here at 6. This way you can change it on the fly if you want to figure out what it would be at 10%. Notice how my formula changed. That's, by the way, where I put my formula. Up here it's just for illustration purposes, but my actual formula is typed in right here. So let's talk about future value. We, of course, need to know our rate. In this case, it's 10%. I could have easily put this in as an actual percentage rather than a decimal. That works as well. We need to know the number of periods. Now, if this is a 10% annual rate, we need to have 6 years. we need to have this stated in years. Now, here is where the confusion sometimes comes about. If we're talking about a payment, we may not be talking about a payment. If we're talking about a lump sum, then there's zero payment. Your only payment is the initial value up front. So I would change that to 0. If this was a annuity calculation, then I would have a payment and it would be negative. The thought here is that money is coming out. If we're talking about the future value, money is coming out of the equation there. So it's going to be a negative. If you try to put in just a positive, the number, it's just not going to make sense. So you always want to think about this to see if it even makes sense. Keep in mind we're solving for a future value here, so we want to know what are we going to have in the future based on all these other components. The present value is the original amount. The day one, what amount are we putting in? In this case, we're putting in $125. The payment is the annual amount. It's if you have an annuity, how much are you putting in each period? In this case, we're adding in $10 each period. So again, if we put in 0, you can see the amount's less by about $70. So not a huge amount, but if we put in that positive amount, it's only $144. It doesn't quite make sense if we invest $125 at 10% interest rate for 6 years, we would expect to have more than about $19 of interest. That just doesn't make sense there. So we know something is wrong, and the answer is that the $10 should have been negative. What this actually means, if we put in $10 positive, we're actually pulling $10 out of our account every year. So there are a lot of things you could do with this. Certainly maybe that is the situation, but for our purposes, we're going to say we're pulling out, or of our own account, we're pulling out $10. We're putting it into the bank. So it's coming out of our cash flow into the bank. That's the way to think about it. Now, as far as type, we could leave it blank. If it's not an annuity, we don't need to worry about it. If it's a lump sum, if we have no payment, then there's no need for a type. This type goes back to the annuity due versus the ordinary annuity that I talked about. 0 means it's an ordinary annuity. The cash flows at the end of the period. If it's 1, that means it's an annuity due. The cash flow comes at the beginning of the period. That's the difference there. So now we know our future value. If we just put in $125 and let it sit there with 0 additional payment, it's going to be worth $221.45. So that is future value. Let's take a look at present value here. So present value I have over here in these additional cells. It's the same idea. You still need to know your rate, your number of periods, your payment. Now you need to know future value instead of present value, because obviously you're solving for present value. Future value has to be the input. And you need to know the type if it's an annuity problem. So it's the same idea. If we type in present value, it'll give you what you need. So our rate is 12% in this case, 6 periods. Again, our payment and our in this case, the future value need to be negative. So what this tells us is that if I have a future value of $125, what is the present value today? If I have no payment, then the present value today is going to be $63.33. So what that means is if I don't wait for the interest to accrue, I don't let it sit around for 12% at 6 years, which would have given me $125, that means I would have $63.33 today. So this is the present value. And again, you can plug in payments to see what that value would be as well. Now let's take it a step further. Let's say it's not really the present value or the future value we're looking for. Instead, we're looking for the number of periods. We don't even know how many years we need to get a certain future value based on a certain present value or anything like that. So as you can see here, there's a separate formula altogether for that. NPER, the number of periods. And I have my references here for the rate, the payment, the present value, future value, and type. I have them all down here. Our rate was 12%. The payment amount is going to be $10, I'm saying. Present value is $10, and the future value is negative $125. So, in this case, I'm going to put in 1, so it's an annuity due. In this case, to have a future value of $125 based on a present value of $10 and payments going in at $10, we would have to have 6.6 years at 12% interest. So I could even take it out. I could have no payment. Whoops, that doesn't work. I could have no payment coming in at all. So if I just had $10 invested and I wanted to somehow turn it into $125 at 12% interest rate, it would take 22.29 periods to get it there. So as you can see here, the more money I put in, that dramatically shortens the number of periods needed. If I put in $10 a year, that's going to get me to my goal more quickly. So that's the number of periods. Now let's say we don't know the interest rate itself. That's what we're looking for here. We know the number of periods, we know the payment, we know the present and future value, we know the type, and then there's a new one listed here called guess. The good news is with the guess, you don't even need to worry about it. You can leave it blank if you want. It'll still calculate it for you. So, again, just like before, if you type in rate, that's the formula for interest rate. If you type in rate, it'll tell you what you need and in what order. So I created this little chart here to refer each of those items of the formula to a cell. So I say we have 6%, or I'm sorry, number of periods we have 6. We have a payment amount that's 10, a present value that's 125, and we have a future value that is 1,000. Now, hopefully you notice a trend here. The present value and future value are going to have opposite signs. The good news is if you try to do something the wrong way, it's going to give you an error. So that'll point you to the fact that something is wrong. So in this case, we want, if we had a $1,000 future value and we had a present value of $125 and payments of $10, somehow we got to $1,000 over 6 periods, that means we must have had a 36% interest rate. That's the only way we could have turned this small amount of money into $1,000 in 6 years. Now, if we only wanted, if we only wanted to turn it into $300 in 6 years, that would have only taken us 10%. So we're solving for the interest rate there. And now we have the final one. This is basically the payment. We're solving for an annuity payment. In other words, we know the rate. The formula here is PMT. We know what the rate is. We know the number of periods. We know both the present and future value. And we know the type. This guess is from the last problem, so don't worry about that. So rate, number of periods, present value, future value, and then type, if it's an annuity, which in this case it is because there's a payment. So our rate was 12%. Our number of periods was 6%. Our present value was $125. Our future value was $1,000. So what we're saying here, in order to turn this present value of $125 into a $1,000 future value and do it over 6 years at a 12% interest rate per year, it wouldn't have done it by itself. This has to be an annuity. If we just invested $125 and expected to get $1,000, it wouldn't work. It would take us longer than this unless we contribute a payment of $82.88 each year. That would get us to our goal of $1,000 at the end of 6 years. That's basically what we're going through here. So that takes us to the end of our discussion for time value of money. Hopefully this information has helped you out a little bit to solve some of your problems, whether it be related to an accounting class you have, a finance class, or just something in general. Thank you for your time, and I look forward to speaking with you in one of the later discussions.